Okay, now I'll talk about something which is related to what we discussed last week, and there were some queries. So I thought, let me type the whole thing in and explain to you. So this will clarify some of the doubts which you had last time. So we'll start simply with particle dynamics, and then we'll see the relevance of what we are discussing with fluid mechanics. So consider a particle of mass m, which is moving, and let us say at time t, it's at a point with position vector, which I'm denoting by the vector r. Now suppose there's a time-dependent external force, which I'm calling capital F, acting on the particle. Now when the particle moves to a neighboring point where the position vector is r plus dr in a time interval dt, what will be the work done by the force on the particle? Well, you know from your mechanics, it is F dot dr. So it is the component of the force in the direction of the displacement, or the component of the displacement in the direction of the force. And if these two are at right angles, there is no work done. Okay. So this is work done on the particle. So I've written this on in red over here. It is work done by the force. Okay. Now I've used the symbol delta W because this in general is not a perfect differential. So delta W is not an increase in work. It represents an infinitesimal amount of work. Okay. So in general, of course, delta symbol might be a finite quantity, but here I'm using it for a infinitesimal quantity. Now if you look at a book on thermodynamics, they'll use D cross W. Okay. Unfortunately, using this Microsoft, I'm not able to get this symbol D cross. Okay. It is not there in the math type. So I have used this symbol, and this symbol is also used in many books on thermodynamics, possibly for the same reason, that writing or typing D cross is difficult. Okay. So delta W represents an infinitesimal amount of work, not a finite amount of work. Now, as I mentioned last time, if the work mode is reversible, this can be positive or negative. If it's irreversible, like frictional force, then it will always have the same sign. Now here we have talked about the work done on the particle. You may be interested in thermodynamics in the work done by the particle. Then that will simply be the negative of this. So work done on the particle is the negative of the work done by the particle. So I will use the symbol delta W with a subscript particle to denote the work done by the particle. So by I have written here in red. It is minus F dot dr, where F is the force acting on the particle. Now let V be the velocity of the particle at time t, as measured by an observer in an inertial reference frame. The displacement of the particle in this time interval dt, as seen by the same observer, will be dr is v dt. And the rate of change of momentum is given by Newton's law, second law. Since we are taking an inertial frame, we can apply Newton's law with the velocity measured in that frame. Okay. Now, if I take the scalar, this is a vector equation. If I take the scalar product of each side with dr, mathematically you will have a simple equation m dv dt dot dr equal to f dot dr. So if this symbol dr represents the displacement of the particle, then this right hand side is the work done by the force when the particle moves from position r to r plus dr. Now suppose at time t1, time instant t1, the particle is at position vector r1, and at time t2 it has moved to a point with position vector r2. So in this time interval t2 minus t1, where t2 is greater than t1, what is the total work done by the force on the particle? If I call it W with a subscript 1 to 2, it is this line integral f dot dr from 1 to 2. And this integral in general will depend on the path followed by the particle. Now F dot dr I can write as m dv dt dot dr, and instead of dr I can write v dt. And if you have v dot ddt of dv, one can write it as ddt of v dot v by 2. Okay, so F dot dr is the mass m into d of ddt multiplied by dt is d of v dot v by 2. Okay, so this integral then is easy to carry out. Okay, so W12 then will be the difference of this quantity m v dot v by 2 at point 2 and point 1. Okay, so you recognize this as the kinetic energy. Now kinetic energy, if I ask you to define what is kinetic energy, you say it is the energy a particle possesses by virtue of its motion. Okay, now how do you find how do you quantify this? That is, what is the amount of the kinetic energy? So if you have a particle traveling with velocity v, suppose it's acted on by a force F which opposes its motion, then the particle will be decelerated to rest. But it will not come to rest immediately. Because it has energy, it will be able to displace the point of application of the force. And in the process, it will do some work. And the work which it can do from the time when you apply the force to the time when the velocity of the particle has become 0, then you can think of as the measure of the kinetic energy of the particle. So if I say capital E with the superscript KIN, if I use this symbol to denote the kinetic energy, then the kinetic energy is this quantity minus integral F dot dr from 1 to 2, where at point 2 the velocity is 0 and at point 1 the velocity was v. Okay, so this is the work done by the particle. So you see that this becomes half mv dot v or half m capital V square, where capital V is the magnitude of the velocity of the speed, which is square root of v dot v. Okay, now yeah, any questions?
Sir, could you mute all? Somebody has his mic on unintentional.
You want me to repeat this part?
No, sir, mute all. Yeah, done.
So I didn't get the question, sorry.
Nothing, sir. I was asking to mute all. Somebody had his mic on unintentionally.
You're talking about the recording?
No, sir. No, nothing.
You have a query regarding any of these equations that I discussed?
No, sir. No, sir.
Okay. Now suppose the particle was initially at rest and is acted on by a time-dependent force which accelerates the particle from 0 velocity to velocity v. This work done by the force is stored as kinetic energy in the particle, and you'll get the same result. Now we are looking at the work done by the force. So you have plus F dot dr, and initial velocity was 0 and final velocity is v. So you get the same quantity. So this is what you may call the work energy relation. W12 I can write as the difference of the kinetic energy at 1 and 2. So the increase in kinetic energy of the particle when it moves from 1 to 2 is equal to the work done by the particle. Now suppose the force is a conservative force, and there were queries regarding this. What is a conservative force? It is one where you can write F as minus grad of a scalar potential, where this potential depends only on the coordinates and is independent of time. Okay, this negative sign is a convention that is put so that you can interpret this as potential energy. Now if you look at the units of E pot, okay, well, when you take the gradient, you have the units of E pot divided by units of length, and left hand side is Newton, and you have 1 upon meter here. So you move it to the right, you see that E potential has the units of force times distance. So it has the units of energy. Now, of course, this also implies that the curl is 0. Okay, So these are some characteristics of a conservative force. Now, what is the work done by the conservative force? Okay, instead of F, I can write minus grad of E pot. So you have dr dot grad E. Now the grad, you know, is del L x Cx plus del L y Ey plus del L z Ez. And dr is dx Ex plus dy Ey plus dz dz. So this scalar product is del L x of E times dx plus del L x of del L y of E times dy plus del L z of E times dz. So if I say E pot depends only on x, y, z, then it will recognize the right hand side of equation 18 as the perfect differential of E pot. Okay. So dr dot grad E will be d of E pot. Okay. Now note this will not be true if it's ER also depends on time, because then there will be another term here which will be del L T of E pot times dt. But del L T of E pot is 0 for us. Okay. So you see that the work done then I can write as minus of d E pot. So in this case, this is a perfect differential. Okay. And if I integrate this from 1 to 2, I'll get E1 minus E2. Okay. So the work done by a conservative force now you see is independent, is a point function. It depends on the thermodynamic state at point 1 and point 2 and is independent of the path. And if you go from 1 to 2 by path gamma 1 and return by another path, this should be gamma 2, sorry. Then the work done will be W12 plus W21. So this I have written as integral from 1 to 2 via gamma 1. And this is integral from 2 to 1 via gamma 2. Okay. Now the first term will be E1 minus E2. And the second term will be E2 minus E1. So you see this is 0. So if the cyclic integral of delta W then is minus cyclic integral of dE pot, which is 0. So these are the characteristics of a conservative force. Okay. Now the important thing is that W12 I can write as E1 potential minus E2 potential. But this we have seen is E2 kinetic minus E1 kinetic. So looking at the middle equation and the last equation, we see that the sum E2 kinetic plus E2 potential at 2 and 1 is constant, and you can call it total energy. So now you understand why we put the minus sign, so that when you transpose this term to the left hand side, you have the sum of two terms, and one you can identify as kinetic energy, and the other one now you can call potential energy. So the work done against a conservative force is stored as what you may call potential energy. Okay. So these are details which I have written for emphasis. You can look at it when I upload the file. Now let us come to the fluid flow. So we are looking at steady flow of an inviscid fluid, which is of course the continuum. Okay. And we're looking at a case where G is constant. Okay. So the balance of momentum is Euler's equation, which you have read in your second year. So for steady flow, the left hand side is simply the convective acceleration times rho. And you have the body force per unit volume on the right hand side and the net pressure force per unit volume on the particle. And this identity, vector identity, I have introduced in the previous class. V dot grad V you can write as minus V cross the vorticity plus grad of V square by 2. Okay. So if I take this and substitute over here, the left hand side I can write as rho of grad V dot V by 2 minus rho V cross omega. Now consider a particle whose volume is dV, infinitesimal volume. Its mass will be rho dV, where rho is the density at the point where the particle is at time t. So if you want the balance of momentum for the particle, okay, not look at the equation of motion which is here. What you get, the link is you multiply both sides of this equation by dV. Then you will have rho multiplied by dV, which is the mass of the particle, times grad of V square by 2 minus rho dV, the mass of the particle, into this V cross omega equal to rho dV, which is the mass of the particle times g. So this is the body force acting on the particle. And the last time minus grad P dV is the net pressure force on the particle exerted by the surrounding fluid due to the variation of pressure on its boundary. Now, recognizing that rho dV is dm, I can write the same equation here where instead of rho dV, I'm writing dm. So the rho dV appears in three terms. And here there is no rho, just dV. So I can multiply and divide by rho and write it as dm times grad P by rho. Okay. And dm will not change with time because it's a particle. The particle doesn't split into two, and two particles will not coalesce. These are inherent assumptions in continuum mechanics. So what we have done is now written the Newton's law for a particle in steady flow when the fluid is inviscid. Now using this you can find the work done. So suppose the particle moves from a point with position vector r to a point with position vector r plus dr in a time interval dt. Okay. Then to get the work done, what you have to do is take this vector equation representing the Newton's law for the particle at time t and take the scalar product with the displacement vector dr. Okay. So then you will have a similar equation, but this was a vector, now this is a scalar, dr dot grad. This was a vector, middle term, it is a scalar. All of them are scalars. And dm is a constant, so if you wish, you can drop it from the equation because each term has dm, but to give a physical feel that this is the energy, this is the equation which shows the balance between the energy of the particle and the work done by the forces, I have kept the dm. Okay. Otherwise, it will become an equation, energy equation per unit mass, and then you'll wonder what it means. Okay. Now V cross omega, will be a vector which is perpendicular to V and omega also. Okay. Now, since the flow is steady, the path line of the particle is a streamline. And for a streamline, you know that dr, which is a tangent to the streamline, will be parallel to V. And if it's parallel to V, it will be perpendicular to V cross omega. Okay. So in other words, dr is V dt and V dot V cross omega is 0. Okay. So dr dot V cross omega is 0 in this case. So note that this is valid because dr is the displacement of the particle, not any arbitrary dr. So it is in the direction of the velocity v. Okay. So the middle term is 0. So what you have now, dr dot grad, you can write as d of v dot v. Why? Because the velocity field is independent of time. Depends only on dr. Otherwise, there will be a term involving del dt of v. Okay. And similarly, if you look at dr dot grad p, this also will be dp because the flow is steady and hence the pressure is independent of time. It is just a function of x, y, z. So for brevity here, I have written p equal to p of r. Okay. So you have a balance of energy equation for the particle in steady inviscid flow. But I have not yet said the density is constant because that was the question which somebody raised in the previous class. So this could be a gas also, a compressible fluid. Okay, this is still valid, but then you have to write it as dp upon rho. Okay, so left hand side you can see is mass times the change of the kinetic energy per unit mass. Okay, so this whole thing is the rate of change of kinetic energy of the particle. Okay, and right hand side is the work done by the gravity force acting on the particle. And the third term is the work done by the net pressure force, net force due to pressure on the particle. Okay. Now since G is constant, G dot dr I can write as d of G dot r. And then if I take this first term on the right hand side and move it to the left hand side, we can combine it with the kinetic energy term. We can write it as dm times the differential of half v dot v minus G dot r. So unit of this is meter per second whole square, which is joule per kg. This also is meter per second square. And right hand side is the work done by the net pressure force. Okay. So you recognize half V dot V as what you may call the specific kinetic energy or kinetic energy per unit mass. So capital E kinetic will be small e kinetic times dm. Okay. Similarly, minus G dot R you will recognize as the gravitational potential energy per unit mass. So if I multiply small e with the superscript GRAV by m or dm, I'll get the potential energy due to gravity on that particle. So the superscript GRAV is to remind you that this is gravitational potential energy. There could be other forms of potential energy also. And if you have a coordinate with the z-axis upwards, vertically upwards, minus G dot R will be plus Gz. So mgz you can recognize as potential energy, and this is half mv square. Okay. So this equation then I can write in this way. This equation as dm times d of E kinetic, small e kinetic plus small e gravity equal to minus dm times dp by rho. Okay. Now suppose the particle moves from point 1 to point 2. Since the flow is steady, the path line of the particle will be identical to a streamline. So therefore 1 and 2 will be points on the same streamline. And let us say 1 is an upstream point at the previous instant of time, and 2 is a downstream point at a later instant of time. Then you can simply say that here what I have done is I dropped the dm. Integral from 1 to 2 of this left hand side is integral 1 to 2 of dp. Okay. So I can write the left hand side as the difference of the specific kinetic energy of the particle plus the difference of the specific gravitational potential energy of the particle equal to minus integral from 1 to 2 of dp by rho. Now if you refer to a book on thermodynamics, you'll see that authors will prefer the variable v, the specific volume, which is 1 upon rho. So I can write it as minus integral of v dp. So you'll see this in books on thermodynamics. Okay. So this is valid even when the fluid density is not a constant. But note that integral dp by rho will depend on the path, except in special cases. So in general, it will depend on the path. Now consider what I talked about last time as barotropic flow. In a barotropic flow, the density depends only on pressure. Okay. Now, one example of this is a liquid where density is a constant. So this function rho of p will be simply a constant. Another example is the isentropic flow of a gas. So if you neglect viscous effects, there is no entropy generation. And if we start with an equation of state, rho is a function of p and s, where s is the entropy, then S1 will be equal to S2. So the change in density of the particle as it moves from 1 to 2 is only because of the change in pressure. So we can call that another example of a barotropic flow. Okay. So now what will happen is, in general, rho will depend on two thermodynamic properties. But if the flow is barotropic, it depends only on pressure. So you are dealing with an integral of this form 1 upon rho p dp. Okay. And if the primitive of this is what I call E with the superscript PRES. Okay. Or in other words, if I introduce a function of P whose derivative with respect to P is 1 upon rho, then dP by rho P is simply the perfect differential d of E with the superscript PRESS. Okay. In that case, this integral for the case of barotropic flow, I can write as this function E at 2 minus the same function EPRESS at 1. So this equation then, which represents the energy balance for the particle in steady inviscid flow. Now if I put another restriction, steady inviscid barotropic, then you will have minus of E2 pressure minus E1 pressure. Now if I transpose this term to the left hand side and write it as the sum of three terms equal to 0, you see what you have is difference from between 1 and 2 of the quantity which I am calling EPRESS plus the difference between 1 and 2 of the quantity which I am calling E kinetic plus the difference of the quantity which I am calling E grav between 1 and 2. Now if I move the quantities with subscript 1, they all have minus sign here. To the right hand side, you will have the sum of E pressure plus E kinetic plus E grav at 2 equal to the same quantity at 1. So therefore now you can say that what I denoted by E with the superscript PRESS, you can think of as a kind of potential energy associated with the pressure. But this is only when the flow is steady and barotropic. Okay. So now somebody had asked the question whether you can call pressure an energy. Well, pressure itself is not an energy. But this quantity, integral of dP by rho, you can interpret as a potential energy associated with the pressure field, but only when two conditions are satisfied. One, the flow is steady, and two, the flow is barotropic. Now, if the flow is not steady, I cannot write this as E2 PR minus this, okay, where these functions depend only on the position. If it depends on time, then we have to find out at which instant of time where the particle is. Okay, but if the flow is steady, then all these quantities in this particular equation and the next one, they just are functions of position. So they are point functions. Now, suppose the density is constant. Okay, then what will be this function? Integral of dP by rho. If rho is a constant, it is simply P divided by rho. So we can conclude that P divided by rho is the kind of potential energy, specific potential energy associated with the pressure field when two conditions are satisfied. One, the density is constant, which is okay for a liquid, and the other is when the flow is steady, that is, the pressure field is independent of time. Okay, so you can call the energy due to pressure as a potential energy, but only in these special cases. It will not be true in general. And the reason I spend this much time is that you may be referring to some books where they make comments on this, and they'll say pressure is not energy, which is true. But you can associate with pressure a potential energy, but only when these two conditions are satisfied. Okay, now any queries regarding this? Okay, now what I'll do then is I'll stop here because it's 11:55, 56 already. And I'll upload these two documents. And in the next class, we'll see what is the application of all this to the Pelton turbine. Okay, so the second document which I opened today is to clarify some of the doubts that you had raised in the previous class. Okay. Are there any other queries? If not, then we will meet tomorrow at 5 p.m. And the other two classes tomorrow will be taken by Professor P.K. Das. He has already sent a mail to you. You must have seen that. Okay, then I am hanging up.